So this is a video going over your check test, which covered the topics of rates and bonding. And bonding, that means the traditional types of bonding, intermolecular bonding, or van der Waals forces as they're known, and also polar, non-polar bonds and molecules. So our first question in the test was, what is the average rate for this reaction between 10 and 20 seconds? And so we have to use the graph. And this is a Nat5 question because it's average rate. So if we look at what we had at 10 and we look at what we had at 20. So average rate is delta Q over delta T. So change in quantity divided by change in time. Our values at 10 was 0.035 and our value at 20 was 0.025. And our change in time is just 20 minus 10. So this works out as 0.01 divided by 10, which is 0.001. And that is equivalent to 1 times 10 to the 3, because 1, 2, 3. And so our answer is B. For our second one, this is a potential energy diagram, so it's showing us the difference. It's asking us what our activation energy is. Now remember, the highest point in our graph is what we would call our activated complex. And our activation energy is our difference between our reactants and our activated complex for the forward reaction, which is what we're being asked about. So our activated complex is X, our reactants are Y, so it's going to be Y minus X. Next question is a bonding question, and it's saying the two hydrogen atoms in a molecule of hydrogen are held together by what? Well, a hydrogen bond is an intermolecular bond, so it's not between two atoms, it's between molecules, so we can rule that one out. Van der Waals forces are, again, intermolecular forces, so they are not between atoms. So we're just left with, is it a polar covalent bond or a non-polar covalent bond? Well, in hydrogen, it's hydrogen bonded to hydrogen. They're the same atom, they will have the same electronegativity, which means that they will be non-polar. For these questions, so we're asked which one has the least ionic. So least ionic means least polar. So we're looking for our smallest difference in electronegativity. So you have to turn to, I think it's page 12 in the data booklet, and look up all those different electronegativities. Now they all have chlorine, and chlorine has an electronegativity of 3.2. So we just need to look at the other ones. So beryllium has 1.6, calcium has 1.0, lithium is also 1.0, and cesium is 0.8. So our smallest difference is going to be between 1.6 and 3.2, which means that beryllium chloride is our least ionic. If you'd been asked for the most ionic, that would have been cesium chloride. So always read the question carefully. This one does require you to have a bit of knowledge from Nat5 to do with the shapes of molecules, because remember, in order for a compound to be polar, it needs to contain polar bonds and it needs to be asymmetric in shape. So I'll draw out the shapes of all these molecules. Carbon dioxide is linear like that. Ammonia is NH3. Now it's just one of those ones where you have to remember its formula is NH3. CCl4 is tetrahedral, and methane, CH4, is also tetrahedral. Now, if you look up the difference in electronegativity between carbon and oxygen, you'll find that this one does have polar bonds. Ammonia has polar bonds because there's a difference in electronegativity. CCl4 has polar bonds, but methane non-polar bonds. There's such a small difference in electronegativity. Then we need to think about, is it symmetrical? And if it's symmetrical, it means it's not polar. Carbon dioxide is symmetrical. So symmetrical. So that means we can't do it. This CCl4 is a tetrahedron, so it's symmetrical. So it is not going to be it, which leaves us with ammonia. And ammonia has a delta negative nitrogen at the top, and then the bottom part is all positive. So it's got a negative end, it's got a positive end, so it is a polar molecule. This is a problem-solving question, and this is a relatively common question that can be thrown in multiple choice. And all this has to do is learning about formula. So carbon dioxide is CO2. For every one molecule, we have one atom of carbon and we have two atoms of oxygen. So if we have 0.5 molecules or moles, we're going to have 0.5 carbon and we're going to have 2 times 0.5, which equals 1 of oxygen. So our moles of oxygen works out at 1. We just take apart our formula and say for one molecule we have 1 carbon, for one molecule we have 2 oxygens. So if we had half a molecule, how many oxygens, how many carbons would we have? Next question is dealing with potential energy diagrams again, but this time it's not asking about activation energy, it's asking about enthalpy change. And enthalpy change is always the difference between your reactants and your products. Remember, your reactants are here and your products are here. It does not matter if it is catalyzed or uncatalyzed. Our enthalpy change, H, or delta H for change, is always going to be our products minus our reactants. So that's going to be 50 minus 100, which gives us minus 50. That minus is important because it tells us that our reaction is exothermic, it will give out energy. And we can always know that a reaction is going to be exothermic if the products have lower energy than the reactants. This next question is again, it's about a difference in electronegativity and then determining which end is going to be positive, which end is going to be negative. Well, hydrogen has an electronegativity of 2.2 and chlorine is 3.2. Now remember, electronegativity is a measure of an atom or nucleus's ability to attract electrons towards it, a shared pair of electrons towards it in a covalent bond. Higher electronegativity means that the electrons are more attracted to that nucleus. So chlorine is going to have the electrons closer to it. So that means we can eliminate B and we can eliminate D because we know that the electrons are closer to chlorine. Now electrons are negatively charged. So if you've got electrons close to you, you're going to be negative, which means that A is our answer, where the chlorine is delta negative and the hydrogen, where the electrons are really far away from it, is delta positive. Relative rates was reached in 1 minute 40 seconds and we've been asked to calculate the rate. So 1 minute 40 seconds, that's not a great time to work out. So 1 minute 40 seconds is 60 plus 40 seconds, which is 100 seconds. Rate is 1 divided by time. So 1 divided by 100 equals 0.1. And we used seconds, so it's seconds to the -1 is our units, which means A is our answer. So remember, we've got two 0.01s in there. If we calculated our time in seconds, our units are going to be seconds to the -1. So this one, elements that contain covalent bonding and London dispersion forces. Now remember, if we've got London dispersion forces, that means we are covalent molecular. So anything that is not covalent molecular, so if it's monoatomic, it can have London dispersion forces, but it does not have covalent bonding. So we're looking for something that is covalent. So London dispersion forces, mean covalent molecular or monoatomic. But the fact that it has covalent bonding means that it cannot be monoatomic. Now, if we look at these ones, boron is a covalent network. So it's not covalent molecular, so it does not have London dispersion forces. Neon is monoatomic. Now that means it does not have covalent bonding. Sodium is a metal. Therefore, it does not have covalent bonds. And sulfur, if we remember, sulfur is S8, which means it is a covalent molecule, and it is our answer. This is the final one of the multiple choice questions, and this is asking us to show which one of these diagrams has a dotted line that represents a permanent dipole interaction between propane molecules. Now remember, permanent dipole means that we've got a delta positive being bonded to a delta negative between molecules. Now if we look at a propane molecule, like this, our carbon-hydrogen bonds, the difference in electronegativity there is about 0.4. So carbon-hydrogen bonds are non-polar, so we don't have any delta positive or delta negative on the CH3 groups. The middle two bonds, carbon to carbon, well, they're the same atom, so we've got no difference in electronegativity there. And it leaves us with this carbon-oxygen double bond. Now, carbon has a lower electronegativity than oxygen, so carbon's going to be delta positive and oxygen's going to be delta negative. So if you look at this first one, we've got oxygen, which is delta negative, to oxygen, which is delta negative. So that one cannot be dipole-dipole because it is negative to negative, and same charges repel one another. In B, we've got delta positive from carbon, but this hydrogen here is non-polar. So that one is automatically ruled out because it's not between a delta positive and a delta negative. It's delta positive to something that's not delta anything. Same with C, we've got hydrogen to hydrogen. Those are not dipole, they're not positive or negative, so that's eliminated. So hopefully in this final one, well, delta negative, delta positive, delta negative, delta positive, our bond is between a negative and a positive, so that is our correct one. So remember, a dipole-dipole, permanent dipole interaction and a hydrogen bond are both between a positive, delta positive part of one molecule and a delta negative part on a different molecule. So now we've gotten into our section 2. Now this first one was a problem-solving question, and it actually required you to do something to the graph before you could actually read off the results. So what you had to do was apply a line of best fit. So your line of best fit would go through all the points. Now, you had one point out here which clearly didn't match the trend, and as a result of it not matching the trend, we just discount it when drawing our line of best fit. It is what we would call an anomalous result. So now that we have our line of best fit, that's when we can look at 10 degrees, go up to our line of best fit, and then across to our values. And we went up 3 boxes. Now, if we look at our scale, each box is going to be worth 5. And so we went up 3 boxes from 150, which means that our solubility is 165. It tells us the units in the question, so we don't need to write any units down. 165. This is an explanation question. And it's saying, and we've been given the difference in electronegativity, and we've been given the shapes of the molecules. And we've also been told that carbon dioxide is less soluble in water. So this question is about polarity and remembering that polar molecules dissolve in polar solvents, non-polar molecules dissolve in non-polar solvents. And the first thing is that we're dealing with water. So we'll write water, remember, is a polar solvent. So we need to specify that. Then let's think about our molecules. So CO2, it has polar bonds. So here has polar bonds. We've got a difference in electricity, but it's symmetrical. So it is non-polar. Sulfur dioxide, SO2, it has polar bonds as well. And not symmetrical, because it's got that bend to it. So that means, so it is polar. And then polar solvents, or polar molecules, sorry, like SO2 will dissolve in polar solvents like water. Or something along those lines. Say, water is a polar solvent, so we'll dissolve polar molecules like sulfur dioxide. You cannot write the phrase like dissolves like. You need to specify that it is a polar solvent dissolving a polar molecule. In this instance, like dissolving like never gets you a mark. A similar question related to polarity. This time, what it's asking us to do is compare which one of those 3 molecules contains bonds with the lowest polarity. So what we are thinking about is the fact that we have chlorine, which has an electronegativity of 3.2, and then we are comparing silicon, phosphorus, and sulfur. Silicon has an electronegativity of 1.9. Phosphorus next has 2.2 and sulfur 2.6. The lowest polarity means the lowest difference. So that is going to be here to here, where it's 0.6. So the molecule with the lowest polarity bonds is chlorine bonded to sulfur. Now our next question here is a 2-mark question, and it's talking about solubility. So explain fully why silicon tetrachloride of those 3 molecules is the most soluble in hexane. Well, just like the last question, let's start with what we know about hexane. Hexane, we just have to remember, is a non-polar solvent. Now, SCl2 and PCl3 have polar bonds. Polar bonds. And are not symmetrical. So that means they are polar. Now if we look at SiCl4, it has polar bonds. In fact, it has the most polar bonds because it's got the biggest difference in electronegativity. But it is symmetrical. It's a tetrahedron with all the same groups around the outside, which means it is non-polar. And then to finish it off, we want a final sentence. Non-polar molecules dissolve best in non-polar solvents. And apologies for my writing. Okay, so hexane is a non-polar solvent. We just have to remember that. Water is polar, hexane is non-polar. Your SiCl2 and your PCl3 have polar bonds. Did that in part 1 of the question. And they are not symmetrical, which means they are polar molecules. SiCl4 has very polar bonds, but it is a symmetrical molecule, which means it's non-polar. And non-polar molecules dissolve in non-polar solvents. This is a rates question, and it's telling us, well, it's collision theory. So collision theory states that for two molecules to react, they must first collide with one another. State a condition necessary for the collision to result in the formation of products. Well, there are two possible answers. So the first one that you could write is they must have correct geometry or orientation. And the second one is they must have energy greater than or equal to the activation energy. So they must have the activation energy and they must have the correct geometry. It only asks you to say one. So our next question, a small increase in temperature can cause a large increase in reaction rate. As temperature is increased, collisions occur more frequently. What other reason is there for the large increase in reaction rate observed when temperature is increased? So we cannot talk about there being more collisions, we have to talk about the other effect that temperature has. And as we increase temperature, remember, we give particles more energy. And if we want to be very specific, that is more kinetic energy. This means more particles will have an energy greater than or equal to the activation energy. So more collisions will be successful. Then that's like an absolute full answer, writing all the words possible. But you say increasing temperature gives the particles more energy, so more will have the activation energy. That's all you'll need for 1 mark. Right, here's another problem solving question. And questions like this, which are worth 2 marks, there's at least 1, if not 2, per paper. So I would go through all the papers from 2016 to 2020. 2021 if that's available. Sorry, 2020, obviously 2021 is not available. Then look at them. They always have the same format. So it's setting up a ratio and then using that ratio. So seaweed contains 0.133 grams of iodine per kilogram of seaweed. So 1 kilogram of seaweed contains 0.133 grams of iodine. Now we want, so the recommended daily intake is 0.15 milligrams. And the question is, how much seaweed gets here? Now, the problem we've got here is that this one's in grams and this one's in milligrams. So we need to know our relationships. So 1 gram is equal to 1,000 milligrams. So in order to turn this, if we multiply by 1,000, this gives us 133 milligrams. And then we can use our, so 1 kilogram, 133, x 0.15. Now this is something where we can use the fish method to do this, where we are going to start at one side and draw a fish, which I always kind of forget how to do, but it's going to be 0. We're going to multiply by 1.5. Our fish is going to go like that. Our fish has a bow tie on, and it's also got a face. Now this one, if we follow it, we've got 1. Might change colour of pen. 1. We get to our bow tie, which means multiply, which gets us 0.15. And then we reach the mouth and eye, which are a divide sign. We divide by 133. And if we put that into our calculator, we end up with quite a small number. So it's 1 multiplied by 0.15, which is obviously 0.15, and then we divide by 133, which gives us 0.00113 kilograms, which is absolutely fine. You could write that in kilograms, or if you wanted to, you can turn that into grams by multiplying by 1,000, which gets you 1.13 grams of seaweed. So this wee fish, it always starts at the number above the thing that you don't know, and it always finishes at the number. So it always goes down and swoops back up. You've got a bow tie and you've got that. If you already know how to work with proportions, you don't need to learn that fish, but that fish trick can help you if you do get stuck. Make sure you put a bow tie on and you put the eye and the mouth on to give you the multiply and divide signs in the correct order. The difficult thing about this one was that we had quite a bit of unit conversions to do. Your final answer, it doesn't tell you what units it has to be in. So if you've worked out in kilograms, that's absolutely fine. Just make sure that you use a good number of significant figures to get the answer. So 0.00133 would be what's sort of needed for that. This question was put into the test because it is one of the most difficult questions that has ever been asked, and the only year it has come up was this past set of exams, where they tried to make the test as hard as possible. So this has only been asked once. Now, London dispersion forces, when it comes to London dispersion forces, remember they're related to electrons. So electrons move around an atom. At any given moment, more electrons may be on one side. So this creates a dipole. So we've got our atom. That means we can have a delta negative and a delta positive side. Nearby atoms are affected by the dipole. Electrons are attracted to the delta positive, or you could say repelled by the delta negative. This induces or creates another dipole. So we had our original atom, delta negative and delta positive. We have our next atom. It's delta negative. The electrons will move to be near to the positive charge or repelled from the negative charge. And this gives you a sort of bond between them. More electrons makes this more likely. So stronger forces. That's a horrible question. So it's all about an atom having more electrons on one side than the other side, which creates the dipole. And then nearby atoms will have their electrons affected by that dipole, which actually creates new dipoles. And you'll have positives attracted to negatives. Those two diagrams, I think, are pretty useful in summing this up. You've got an atom with a delta negative, a delta positive, and then a nearby atom will have a new dipole induced. It's a horrible question. It's definitely an A-type question. Right. Next question is about London dispersion forces, and it's asking why are they stronger in sulfur than in oxygen? Now, to get both marks for this, you have to talk about what is the difference between sulfur and oxygen in terms of structure and bonding, and why does that difference mean that the London dispersion forces are stronger, or what is it that makes London dispersion forces stronger? So LDF, we know this, are stronger for atoms or molecules with more electrons. We know that. Just by saying that, you are showing that you understand what affects London dispersion forces. So you can get 1 mark potentially just for writing that. Then let's just think about it. Oxygen is diatomic. O2. Sulfur is S8. Sulfur has, oh, bad writing, has more electrons than oxygen because it is bigger. Sulfur has stronger LDFs. So I know you're basically saying the same thing twice, but clarifying that London dispersion forces are affected by electrons, and the number of electrons, then explaining why sulfur has more electrons than oxygen to conclude that's the reason it has stronger London dispersion forces is the best way to answer this question. Right, from this graph, indicate the reaction time in seconds when the concentration was 1 mole per litre. Well, what we need to do is look at 1 mole per litre and read across to what's on our y-axis. Now, if we look on our y-axis, that's relative rate. What we've been asked for is our reaction time. So please don't just write 0.022. There's a step needed to do this. So time is equal to 1 over rate. So remember, rate is equal to 1 over time, time is equal to 1 over rate. So what we're going to have here is 1 divided by 0.022, which gives us 45.45 repeating seconds, or if you wanted to round that up to 1 decimal place, that would be acceptable. Either one of those is fine. Next question. So the rate of reaction can be altered by changing the temperature or using a catalyst. Graph 1 shows the distribution of kinetic energies of molecules in a gas at 100 degrees Celsius. Add a second graph at 50 degrees. So our original one is 50, so we have decreased temperature. So remember, that means it's going to get taller and thinner. We always start our graph at the same point. So it always starts at 0, 0. We need to make it taller and we need to make it thinner. So it finishes earlier than the first graph and it has to be taller. As long as it is a little bit taller and finishes a little bit earlier, you will get the mark. If your graph is the same height, you cannot get any marks. You must show it being taller and you must show it being thinner. Next question is, it's the same thing, but it's saying if you add a catalyst to this, what happens to the activation energy? Well, we know that activation energy gets lowered, so as long as you've drawn a line on it that is to the left, you have shown the activation energy to have gotten smaller. If you label it new activation energy, then it makes it very, very, very clear. Final set of questions we had was again related to the potential energy diagrams, but this one is more problem solving. So the first question is unstable arrangement of atoms, and it's pointing to the tallest part of that graph. So the tallest part of that graph is always our activated complex. So the tallest part is always the activated complex. The second question is a bit odd. It's asking us for enthalpy change for the forward reaction. So that, remember, is our difference in energy between our reactants and our products. Now, we've not been given information about the energy of our reactants or about our products. However, we have been told what the activation energy is before going between our reactants and our activated complex and our products and the activated complex. So our enthalpy change is actually going to be our difference between these two numbers. So it's going to be 182.8 minus 173.2, which gets us 182.8 minus 173.2 equals 9.6. And we do need to think about, does it have a negative sign or does it have a positive sign? Well, our products are lower than our reactants, so this is exothermic. So we need a negative sign to show that. That's a very hard way of asking you to work out the enthalpy change, but it can be done. If you know the activation energy of the forward and the reverse reaction, the enthalpy change is the difference in activation energy between those two processes. And then you just choose the sign based on whether the products are lower than the reactants or the reactants are lower than the products. In this case, because products have less energy, it's exothermic, so we need a negative sign. So that has been us going over rates and bonding and polarity. I know this is a 40-minute video, but I think going over in detail the explanations for each answer is important, and hopefully by watching this you can do really well in your upcoming September test and then in any subsequent test in which you can again watch this video. Okay, so thank you for watching. I hope this is useful.